On the 21st of January 2000 at 3:50 p.m, a McDonnell Douglas MD83 flies above the Pacific Ocean, about 25 miles off the Californian coast of the United States. Alaska Airlines Flight 261 departed from the international airport at Puerto Vallarta, Mexico, about 2.5 hours ago, bound for the United States. Its first planned stop is San Francisco, California, before its final destination of Seattle in the state of Washington. On board the flight are 83 passengers and 5 crew members. As well as the 5 crew members of Alaska Airlines working today, an additional 25 passengers are connected with the airline in some way. It is common for Alaska Airlines to use underbooked flights to transport their personnel. Today, the McDonnell Douglas MD83 is being crewed by 2 highly experienced pilots. The captain, Ted Thompson, aged 53, is an Air Force veteran who has amassed nearly 18,000 hours of flight experience. He has more than 4,000 hours as pilot in command of the MD-80 series of aircraft. He is supported by First Officer Bill Tansky, aged 57, with more than 8,000 hours flight experience, almost all of which have been at the controls of the MD-83. Bill Tansky, an Air Force veteran, is 2 years away from retirement from Alaska Airlines after a successful flying career. The MD-83 they are piloting today is derived from the venerable DC-9, with the fuselage being lengthened, more fuel-efficient engines being fitted, and advanced avionics being provided. At this moment, a crisis is unfolding in the cockpit, which had its origins years earlier. What has started as a routine flight will turn into a battle between the pilots and the aircraft, which will destroy them both. You are listening to Inside the Black Box. This is the story of Alaska Airlines Flight 261.
Pull up! Pull up!
A little over 2 hours earlier, at 1:37 p.m, Alaska Airlines 261 thunders down the runway without incident, as the aircraft has done more than 14,000 times since it entered service. Three minutes after takeoff, at 6,200 feet, First Officer Bill Tansky, who is piloting the aircraft, activates the MD-83's autopilot. The autopilot will continue the climb to the aircraft's cruising altitude of 31,000 feet. The MD-83's autopilot will make small adjustments to the aircraft's control surfaces to maintain a cruising climb speed of about 330 knots. 13 minutes after takeoff, the pilots notice something unusual. The aircraft's speed has begun to drop. It falls steadily from 331 knots to 269 knots. At the same time, a warning light in the cockpit illuminates that the aircraft is out of trim. In aviation, an aircraft is trimmed to neutralize the control inputs needed by a pilot for a specific task. For example, if the aircraft is climbing, instead of the pilots having to continuously pull back on the control column to maintain the climb, they can trim the aircraft so that it will continue its ascent without any additional input from the pilots. Trimming an aircraft's vertical motion is achieved in a number of ways and depends on the type of aircraft. In the MD-83, it is accomplished by moving the entire horizontal stabilizer. The horizontal stabilizer is located on the tail of a conventional commercial aircraft and is designed to keep the aircraft stable in flight. The MD-83 is what is known as a T-tail configuration, with its horizontal stabilizer mounted on the very top of the aircraft's tail fin, forming a T-shape. On the MD83, this design has been chosen because it keeps the tail clear of the jet blast from the aircraft's engines, which are located on the side of the fuselage. When the pilot, or the MD83's autopilot, wishes to trim the aircraft, the entire horizontal stabilizer will pivot up and down, altering the airflow and generating more or less lift. When the pilots are flying, they will manually trim the aircraft until the control forces they are feeling disappear. With the aircraft's autopilot, if the elevator is in the same position for 5 or more seconds, the autopilot will command the horizontal stabilizer to move. The MD83's out of trim warning activates when the autopilot has commanded that the trim be adjusted, but the horizontal stabilizer has not moved for 10 seconds following the command. In response to the reduction in airspeed and the trim warning, at 28,500 feet, the pilots disconnect the aircraft's autopilot and begin to fly the MD83 manually. However, upon disconnecting the aircraft's autopilot, First Officer Tansky finds he has to pull back hard on the aircraft's control column in order to keep climbing. He needs to apply approximately 50 pounds of pulling force in order to keep the aircraft ascending. First Officer Tansky attempts to trim the aircraft to reduce the force required, but the trim doesn't respond. Alaska Airlines 261 continues its climb, although at a much slower rate than before the autopilot was disconnected. 24 minutes after disconnecting the autopilot, and at 31,000 feet, the pilots level off. Now the aircraft is flying level, the forces required by First Officer Tansky to maintain the aircraft's altitude has decreased. It now only requires 10 pounds of pulling force on the control column. Although the situation is far from normal, it does not appear immediately dangerous. However, it is concerning the pilots. For the next hour and 20 minutes, Alaska Airlines 261 continues its northwesterly course, tracking over the Pacific Ocean. While First Officer Tansky continues to fly the aircraft, Captain Thompson works to diagnose the problem. Whenever Captain Thompson or First Officer Tansky try and activate the aircraft's vertical trim, there is no response. Given they are not able to adjust the aircraft's horizontal stabilizer to trim the aircraft, they conclude it is most likely the horizontal stabilizer which has jammed in place. At 3:47 p.m., 2 hours and 10 minutes after taking off, the pilots reactivate the aircraft's autopilot. 3 minutes later, Captain Thompson makes contact with Alaska Airlines ground personnel. Alaska Airlines Flight 261 is using a shared frequency between their dispatch and maintenance center based in Seattle and the operations and maintenance center based at LA International Airport. Captain Thompson informs the dispatcher in Seattle that they have experienced a jammed horizontal stabilizer and discuss a possible diversion to Los Angeles International Airport. The dispatcher in Seattle questions Captain Thompson as to why he wishes to land at LAX instead of San Francisco as planned. Captain Thompson replies that often the weather is windy and wet at San Francisco, and given the condition of the aircraft, a dry runway where the aircraft would be flying into a headwind would be more reasonable. The Alaska Airlines dispatcher in Seattle relays the weather at LAX to the pilots of Alaska Airlines Flight 261. He then goes on to say that should the pilots wish to divert to LAX, this will cause a significant flow problem for the airline. As a company, Alaska Airlines needs to manage the transfer of passengers scheduled to land at San Francisco and Seattle. Delays will require these passengers to be booked onto alternative flights, costing the airline time and money. Captain Thompson tells the dispatcher he doesn't want to hear about flow problems given the condition of his aircraft. He requests further information on the wind direction and speed and runway conditions at San Francisco Airport, and requests assistance from a ground instructor who may have more ideas about what to try to unjam the MD83's horizontal stabilizer. In the cockpit and off the radio in private, Captain Thompson expresses his frustration to one of the flight attendants about Alaska Airlines dispatch discussing their flow problems. He tells the flight attendant, "It just blows me away that they think we're going to land, they're going to fix it. Now they're worried about the flow. I'm sorry, this aircraft's not going to go anywhere for a while." The Alaska Airlines dispatcher at Seattle comes back with the weather at San Francisco Airport. The current runways being used are 28 right and 28 left. Runways are numbered based on the direction they are facing on the compass. In the case of runway 28 right and left, these runways are facing almost directly west. The wind is reported as coming from 180 at 6, meaning there is a 6-knot wind coming from the south. This means that the aircraft would be landing in a slight crosswind at San Francisco Airport. The Seattle dispatcher then tells the pilots that the wind at LAX is 260 at 9, meaning that there is a 9-knot wind coming from the west. Captain Thompson considers his options and selects the landing which will allow him to touch down with as much headwind as possible. A headwind is advantageous for landing because it means the aircraft's speed relative to the ground can be lower as it touches down, since a component of the airflow required to generate lift is made up by the wind. Captain Thompson knows that if he lands at LAX, he can land using runways 24 or 25, which are pointing almost directly west, straight into the wind. With this information, Captain Thompson decides it would be best to divert to LAX. Upon making this decision, he contacts LAX and asks for assistance with their center of gravity calculations for landing. As the ground personnel make these calculations, a maintenance technician at LAX contacts the pilots in an attempt to assist them. The technician asks Captain Thompson if he has tried both the MD83's pickle switches and suitcase handles. The MD83's trim is normally adjusted by small buttons on the pilot's control wheel, known as the pickle switches. Alternatively, if these switches do not work, the pilots can use levers on the MD83's center pedestal, known as suitcase handles, to adjust the trim. Captain Thompson confirms he has tried both sets of switches, and states they get a spike on the AC load meter whenever they try and adjust the aircraft's trim. The load meter compares how much current is being drawn compared to what the aircraft's generators are capable of providing. The spike indicates the trim system's motors are trying to move the MD83's horizontal stabilizer, but without success. The maintenance technician tells Thompson that he will look on the ground for any other circuit breakers that might assist the pilots in moving the stabilizers or explaining why it is jammed. Captain Thompson decides to try the aircraft's trim switches on the control wheel, or pickle switches, once again. Referring to the aircraft's autopilot, he tells First Officer Tansky, "This'll click it off. You got it?" When the trim system is working normally, activating the trim controls will disconnect the autopilot. Tansky confirms he is ready to take control of the aircraft in the event of the autopilot disconnecting. Captain Thompson presses on the pickle switches. At 4:09 there is a sound of a clunk, followed by 2 faint thumps in quick succession. Immediately, the stabilizer motion warning begins sounding in the cockpit. In parallel, the MD83's nose drops, and the aircraft enters into a steep dive. First Officer Tansky exclaims, "Holy shit," as the MD83 starts rapidly descending from 31,000 feet.
Altitude. Altitude.
The MD83's altitude warning starts, indicating the aircraft has left its preset altitude. As the aircraft's speed builds, it begins to shudder, reacting to the stronger aerodynamic forces. Both pilots pull back on their respective control columns, but it requires an enormous amount of effort to fight the steep dive. Thompson orders the deployment of the aircraft's speed brakes in an attempt to arrest the aircraft's rapidly building speed. The MD83 begins to pitch up, but its descent continues. Captain Thompson contacts LAX and informs them that they are in a dive and they have lost vertical control of their aircraft.
Overspeed. Overspeed.
A clacker sounds in the cockpit,
Overspeed.
followed by the overspeed warning,
Overspeed.
telling the pilots the aircraft is reaching the limit of its structural integrity.
Overspeed.
If they do not arrest the speed of the aircraft, the aerodynamic forces will tear the aircraft apart.
Overspeed.
But with both pilots pulling back on the control columns, the aircraft finally comes out of the dive and begins to level off. In all, the dive has lasted 80 seconds, and the MD83 has fallen about 7,000 feet, now flying at 24,000 feet. Alaska Airlines Flight 261 appears to be under control. The pilots both agree on the cause of the dive. The MD83 is suffering from runaway trim. This occurs when the aircraft's trim surfaces adjust without being commanded by the pilot or the autopilot. In this case, the trim surfaces are now doing the exact opposite of what they are designed to do, that is to reduce the workload on the pilots to fly the aircraft. Now, the pilots find themselves having to fight against the trim just to maintain altitude. In this case, it is clear to the pilots that the trim has run away nose down, so that they now must pull back with an enormous amount of force just to keep the aircraft flying straight and level. Both Captain Thompson and First Officer Tansky agree that the aircraft is in much worse shape than they had previously thought. The pilots discuss whether they should try and adjust the aircraft's trim again to try and relieve some of the pressure they are having to maintain on the control column just to maintain level flight. Although this is tempting, and the pilots believe the horizontal stabilizer might have reached the limit of its travel, they also weigh up the risk that the situation could become worse. Thompson decides to take this moment to brief the passengers in the rear who have just been subjected to the steep and obviously abnormal dive. Thompson states, "Folks, we've had a flight control problem up here. We're working it. That's Los Angeles on the right there. That's where we're intending to go. We're pretty busy up here working the situation, and I don't anticipate any big problems once we get a couple of subsystems on the line, but we'll be going into LAX, and I'd anticipate us parking there in about 20 to 30 minutes. Captain Thompson contacts LAX Center and communicates their intentions to land. The captain tells LAX Center that he wishes to descend to 10,000 feet and configure the jet for landing, and he wishes to do that over the bay. First Officer Tansky calls one of the aircraft's flight attendants to the cockpit. Captain Thompson instructs them to put anything loose in the cabin away and have everybody in their seats. Before leaving, the flight attendants tell the pilots they heard a loud bang in the rear of the aircraft, further confirming an issue with the horizontal stabilizer. Captain Thompson states he wants to try and pull the aircraft's nose up, then let the nose drop down while he adjusts the horizontal stabilizer. The intention is to reduce the aerodynamic forces on the horizontal stabilizer before trying to trim it again. First Officer Tansky does not believe this is a good idea, and that if the aircraft can fly, they should just try and land it. Captain Thompson agrees and says, "You think so? Okay, let's head for LAX." Alaska Airlines 261 has been given a block altitude, meaning it can operate at a range of altitudes without seeking permission from air traffic control. The air traffic controller at LA has asked a number of aircraft in the vicinity to maintain visual contact with Alaska Airlines 261. The pilot of an Aero Commander 690 light turboprop is the first to spot Alaska Airlines 261 in what will become its final moments. The pilot watches the MD83 flying normally. Suddenly, Alaska Airlines 261 rapidly noses down into an almost vertical dive as it begins to roll. A moment later, the pilot of SkyWest Flight 5454 also spots the aircraft. The following is a recording of the conversations between the pilots and the controller at LAX.
Hi, 0 Delta X-ray. That plane has just started to do a big, huge plunge.
A big, huge plunge. Thank you. SkyWest 5154. The MD80 is one becoming about 2 o'clock, about 10 miles now. Another pilot reports he's really looking pretty bad. They're heading to your right. Do you see him?
Yes, sir. I concur. He is definitely in a nose-down position, descending quite rapidly.
Okay, very good. Keep your eye on him. Alaska 261, are you here with us yet, sir?
Plane's inverted, sir.
Okay, very good. It looks like he's turning over in front of you now, SkyWest 5154. You still got your eyes on him, sir?
There is a sight. He definitely out of control.
Okay, very good.
Yeah. Yeah, he's inverted.
Okay. Just do what you need to do there, SkyWest 5154. Keep us advised.
And he's just hit the water. Yes, sir. He hit the water. He's down.
Okay.
And for position, I'm right abeam of 50 Delta X-ray.
Yeah, he just now hit it. We have the spot marked right here. Thanks, guys.
At just before 4:21, the MD83 slams into the Pacific Ocean. Alaska Airlines 261 has hit the water flying inverted at about 200 knots. The MD83, with 88 souls on board, disintegrates on impact. The United States Coast Guard immediately responds, dispatching a fleet of boats and aircraft to the crash site, which sits about 14 miles off the coast of California. Within an hour, the first vessels begin arriving. They are supported by local boat owners, fishermen, and the US Navy in scouring the area for any survivors. They arrive at the scene as daylight is fading. Throughout the night, the rescuers search for any survivors of the accident. Meanwhile, a full National Transportation Safety Board GO team is assembled in Washington, tasked with investigating what has brought down Alaska Airlines 261. They arrive in California the following morning. The morning following the accident, the US Coast Guard holds a press conference outlining the efforts that have been made in the search for survivors. Unfortunately, in spite of these efforts, the rescuers have recovered no survivors. As the day progresses, it becomes clear that the rescue efforts have been in vain. The 83 passengers and 5 crew members of Alaska Airlines Flight 261 have perished. Alaska Airlines 261 crashed in an area of water about 700 feet deep. While the surface recovery of bodies and floating debris continues, the search for underwater wreckage was begun. The NTSB employed side-scan sonar, which we discussed in our previous episode on Air France 447. The side-scanning sonar helped the investigators build an image of the sea floor beneath them. The wreckage of Alaska Airlines 261 has come to rest 700 feet below the surface, with the debris covering about a quarter of a mile, a fairly small debris field. Once the subsea search area was established, remotely operated vehicles were sent to the sea floor to recover the bodies of the victims and the wreckage. The sudden impact with the water has been catastrophic for the aircraft as well as those travelling in it. Almost all of the bodies have broken apart. The victims' remains were transported to the Ventura County Medical Examiner. There, using DNA, dental records, tattoos, or any other distinctive features, the victims of the accident were slowly confirmed. When bodies were returned to grieving families, they would often be delivered in batches, as more parts were found and subsequently identified. In recovering the wreckage, the ROVs either loaded the parts into baskets which were winched to the surface, or attached cables to the larger pieces of wreckage, such as the engines, and lifted them from the sea floor. Crucially, both the aircraft's cockpit voice recorder and flight data recorder were recovered after 2 days of the accident and sent to the NTSB's laboratories in Washington for analysis. Towards the end of the recovery operations, the NTSB employed a commercial fishing trawler to gather smaller pieces of wreckage using its nets. 15% of the entire wreckage was recovered in this manner. The recovered fuselage segments increased in size from the forward section of the airplane, where they were the smallest, to the aft section, where they were largest. This indicated to the investigators that the aircraft had been travelling nose down on impact. The largest sections of the aircraft were from below the airplane's floorline. Since the aircraft had been flying inverted as it hit the ocean, the bottom of the aircraft had not been subjected to so severe an impact. Given the final broadcast from the pilots, and the aircraft's performance in its final moments, the NTSB are fairly certain where to begin their investigations, at the tail of the aircraft. But they have a number of questions to answer. First, why had the horizontal stabilizer jammed? Next, what had caused the initial dive that the pilots were able to recover from? Finally, what had caused the final dive, which led to the loss of Alaska Airlines 261? The investigators looked at the wreckage that made up the rear of the aircraft. Both of the MD83's engines, which are attached to the rear of the fuselage and below the tail, were recovered. While the aircraft's number 1 engine, which sits on the left of the aircraft, appeared to have been generating power as the aircraft impacted the ocean, the number 2 engine on the right did not appear to be rotating at the time. An engine failure wouldn't lead to such a dramatic accident though, so the investigators believe this to be a consequence of some other failure rather than the main failure itself. The most important wreckage to be recovered was the parts which made up the MD83's horizontal stabilizer, which the pilots had reported as jammed, then running away shortly before impact. The horizontal stabilizer has been badly fragmented, but most of it is recovered from the sea floor. However, as the investigators recover the wreckage of the badly fragmented stabilizer and piece it together, they notice that something is not as expected. Before continuing any further, we need to understand what causes the MD83's horizontal stabilizer to move up and down when the pilots or the autopilot adjust the aircraft's trim. The movement of the stabilizer is controlled by what is known as a jack screw assembly. Picture a bolt with a nut threaded about halfway into it. Now imagine that you hold that nut steady and spin the bolt. The bolt will travel up and down and move higher and lower relative to the nut. On the MD-80 series of aircraft, the top of that bolt is connected to the horizontal stabilizer. The bolt is actually called a jack screw. The horizontal stabilizer pivots from the rear, so that when the jack screw assembly moves upwards, this causes the aircraft's nose to pitch downwards, and vice versa. Instead of the nut being held in between our fingers, it is attached to the vertical stabilizer, the large fin at the rear of the aircraft. This is how it remains stationary. The nut is called an acme nut. The acme term comes from the distinctive trapezoid-shaped threads which it uses. This shape is easy to manufacture and is also very strong. At either end of the jack screw are 2 mechanical stops, which prevent the jack screw from rotating itself free from the nut in the event of a malfunction. The acme nut is effectively trapped between the 2 mechanical stops, which dictate the limit of the jack screw and therefore the horizontal stabilizer's motion. When the pilot or the autopilot adjusts the vertical trim, a motor at the top of the assembly rotates a torque tube. The torque tube runs from the motor through the jack screw and out the other end. Whenever the torque tube is rotated, this also causes the jack screw to rotate up or down through the nut and adjust the angle of the horizontal stabilizer, causing the aircraft to trim up or down. There are actually two motors which can turn the jack screw. The primary motor, which the pilots use to manually trim the aircraft, and the alternate motor, which is used by the autopilot and works more slowly. The jack screw is made of case-hardened steel and is very strong. In contrast, the acme nut, which the jack screw runs through, is made of a softer aluminium-bronze alloy. The acme nut is what is known as a wearing component. It is designed to eventually wear out and requires regular lubrication to reduce this wear. Eventually, when the acme nut wears down to a certain level, the nut is replaced. The nut is normally coated with grease to reduce friction and wear on the part. When looking at the components of the horizontal stabilizer, even after such a catastrophic descent into the ocean, it was clear to the investigators that something was very wrong with the components of the jack screw assembly. The first and most obvious issue is that the jack screw and the acme nut are found separate to each other. The jack screw is found attached to the wreckage of the horizontal stabilizer, while the acme nut is found several meters away, still attached to the vertical stabilizer. The next anomaly is what appears to be metal fibers wrapped all the way round the jack screw itself. Finally, and perhaps most telling, the investigators look at the bottom of the torque tube which juts out below the jack screw. It has been completely severed. An image was building in the investigators' minds of what had happened to the aircraft, but the exact failure sequence still needed to be determined. Initially, the recovered wreckage was examined at a dockside facility in California. After the on-scene examinations concluded, laboratory examinations were conducted at the Safety Board's Materials Laboratory in Washington, the Boeing Commercial Aircraft Materials and Process Engineering Laboratory, and Integrated Aerospace in Santa Ana, California. First, the metallurgists looked in greater detail at the aircraft's jack screw. The most obvious issue was the metal strands which were wrapped around it, since these were definitely not part of the jack screw's design. The metallurgists examined the directions the strands were travelling in, and noted that they were in line with the threads of the jack screw. They also studied what these strands were composed of, determining that they were made of an aluminium-bronze alloy which had turned green from saltwater corrosion. From this, it was clear that these strands were the remains of the threads of the acme nut. Somehow, these threads had been completely stripped out of the acme nut. The jack screw and acme nut actually have two sets of independent threads, which means that if one set of the threads fails, there is another to take its place. But both threads appear to have failed at once. How could the threads have disintegrated? The investigators looked at the acme nut and jack screw together. There was a component which was conspicuous in its absence: a means of lubrication. Lubrication is essential where metal acts on metal in mechanical applications such as gears. The lubrication greatly reduces the wear on the components. The investigators would expect to see the components coated in grease to allow them to move smoothly and minimize wear. But the only grease to be found is hard and dry, which would not have aided in lubrication. The investigators look at the grease nipples and grease passages which lead to the interior of the acme nut, where the threads are to be found. They too are devoid of any grease. To ensure the grease is not simply washed away while it was submerged, the the investigators performed experiments, simulating the environment the jack screw assembly had been in while it was submerged. Even after several days of being submerged in salt water, the grease remained on the components. This confirmed to the investigators that there was no grease on the components at the time of the accident. With no lubrication, the case-hardened steel of the jack screw would have worn down the softer metal of the acme nut much faster than the designers would have expected, as metal ground against metal. After looking at these components, the investigators considered how the trim system had performed as expected during the initial climb of the aircraft before becoming jammed. While they couldn't be certain, the investigators believed that the most likely cause of the jam was the threads of the acme nut beginning to deform between the jack screw and the nut's body. This explained why the trim system had worked initially, before failing as the aircraft continued to climb. Once the horizontal stabilizer had jammed, the force of the motors from either the primary or alternate trim systems was insufficient to counter the jam. But over time, the aerodynamic loads coming from the horizontal stabilizer and the repeated use of the trim system began to deform the damaged threads further and further. Eventually, when Captain Thompson applied the primary motor for a final time, the threads were finally completely sheared and the jam was relieved. With the threads of the acme nut destroyed, the nut now served no purpose in holding the jack screw in place. Alaska Airlines 261's trim control was now completely ineffective. More seriously, the jack screw and the horizontal stabilizer it was attached to was now free to move of its own volition. Instead of the jack screw driving the movement of the horizontal stabilizer, it would now be the horizontal stabilizer moving the jack screw. This was not a situation the designers of the aircraft had ever envisaged. It was always assumed that at least one set of threads would remain intact and take the load. The aerodynamic forces acting on the horizontal stabilizer pushed it backwards. This caused the tail to generate more lift and pushed the nose of the aircraft down. This sequence of events was the cause of the initial thump heard by the pilots and explains the sudden first dive that Alaska Airlines 261 experienced. The horizontal stabilizer only stopped moving when the mechanical stop at the bottom of the jack screw struck the acme nut, holding it in place. The strength of the jack screw and the torque tube within it was now all that was holding the horizontal stabilizer in place. The investigators turned their attention to the fracture at the end of the torque tube, which protruded below the jack screw. The tube showed signs of low cycle fatigue, having failed over a fairly small period of time. In addition, the tube had been bent. This provided metallurgists a further clue as to what had led to Alaska Airlines 261's final plunge. When the threads on the acme nut had been intact, the aerodynamic forces from the horizontal stabilizer were transferred through the jack screw's threads to the acme nut. But with those threads gone, and the lower mechanical stop resting against the bottom of the acme nut, all of that force was now being borne by the jack screw and the torque tube which ran through it. The lower mechanical stop was not perfectly round, but instead had lugs which protruded up from its surface. When the stop contacted the bottom of the acme nut, the pressure wasn't uniformly transferred to the jack screw and torque tube. Instead, the assembly began to be deformed at its weakest point, the point where the jack screw ended and the torque tube protruded below it. The torque tube would be repeatedly strained as the horizontal stabilizer reacted to the aerodynamic forces acting upon it. With these repeated loads, compounded by the uneven pressure being applied by the lower mechanical stop, the torque tube slowly grew weaker. Eventually, these forces proved too much. The torque tube finally fractured, removing the lower mechanical stop and allowing the entire jack screw and torque tube assembly to travel up through the acme nut. The last component which explains the sequence of Alaska Airlines Flight 261's final moments is the vertical stabilizer tip fairing. This is the surface that sits on top of the MD83's tail, making the tail more aerodynamic. It has been found broken into several pieces. The front of the tip fairing is completely missing. As the jack screw assembly had travelled upwards, it hammered against the fairing. Having never been designed to maintain the sort of structural load which it was experiencing, the front of the fairing completely disintegrated. This finding was backed up by the small radar signatures being recorded at about the same time as the final dive began. These radar signatures being components of the tip fairing. With the fairing completely destroyed, the last impediment to the movement of the horizontal stabilizer was removed, and it was free to continue to pivot backwards. This caused the tail to suddenly generate a great deal more lift, forcing the nose of the aircraft down into a dive from which it would never recover. The investigators understood the accident sequence, but this only raised more questions. How could the aircraft's acme nut, which was the wearing part that required maintenance and replacement, have been permitted to get into a state where all the threads could strip out? The metallurgists looked at the strands of the acme nut threads which remained, and determined that about 90% of their thickness had already been stripped away before they finally sheared off. As discussed earlier, the jack screw and acme nut were found completely devoid of any lubrication. Only old and dry grease was present. It seemed inconceivable that regular maintenance would not have lubricated the acme nut or identified that the acme nut required replacement. In order to understand how the badly worn jack screw was ever allowed to be on Alaska Airlines 261, we have to look back at the history of the airline and the aircraft itself. Alaska Airlines had been formed in the 1930s, but by the 1970s it was on the brink of collapse. It was one of only 3 airlines in the United States which supported the deregulation of passenger aviation, knowing that this would increase the number of aviation routes and destinations. Following deregulation, and with creative marketing and high-quality service, the airline was able to carve out a market in the Pacific Northwest of the United States of America. But the rising levels of competition within the airline industry from low-cost carriers such as Southwest Airlines forced the airline to begin to cut costs. There was also a very large seasonal imbalance for the airline in the area in which it operated. Much of its business in the Pacific Northwest was conducted during the warmer summer months. So in order to address this, Alaska Airlines introduced routes to destinations such as Mexico, including the route Alaska Airlines 261 would eventually fly on. This allowed the airline to increase the utilization of its aircraft, flying more flight hours per year. During the 1990s, in order to remain competitive, further cost-cutting measures led the airline to delay the purchase of new aircraft, and instead increase the utilization of its current fleet. But the increased utilization brought about by flying the same aircraft more often put enormous pressure on the airline to keep the existing fleet in service. This pressure was being felt by some of the mechanics who worked for Alaska Airlines and maintained their aircraft. They claimed that they were being coerced into signing aircraft off as airworthy in order to get them back into service, even when maintenance might not have even been completed. In October 1998, before the disaster of Alaska Airlines 261, a senior mechanic working for Alaska Airlines, John Leotine, wrote to the Federal Aviation Administration, voicing his concerns on Alaska Airlines' maintenance policies. This led to a federal grand jury investigation of Alaska Airlines, centering on allegations that superiors were signing off work that had never been completed. Although no criminal charges were filed, The FAA found hundreds of maintenance irregularities with Alaska Airlines records. John Leotine, for his actions as a whistleblower, was put on paid leave and eventually resigned from the company. The last time the Acme nut should have been lubricated was in September 1999, about 4 months before the accident. The NTSB interviewed the Alaska Airlines mechanic who had been responsible for the task. He stated that the procedure to lubricate the jack screw assembly should take about an hour. In comparison, Boeing, who now manufactured the MD83, stated that the task should take maintenance personnel 4 person-hours. The mechanic also stated that he did not recall checking to see if grease was coming out of the top of the Acme nut, as specified in the general lubrication guidance. The investigators also inspected other Alaska Airlines MD83s which had been serviced by the same mechanic. All the aircraft they inspected were noted to have higher than expected wear rates on the jack screw assembly. It was clear that through either misunderstanding or negligence, the mechanic who had lubricated the jack screw on Alaska Airlines 261 had not adequately performed the task, or not performed it at all. Although they couldn't confirm it, the complete lack of any lubrication suggested to the investigators that more than one opportunity had been missed to lubricate the assembly. Not only had the jack screw been inadequately lubricated, the opportunities to lubricate the jack screw had become rarer as time went on. The NTSB looked at the frequency with which the lubrication was to be carried out, per Alaska Airlines policies. In aviation, checks on aircraft are often divided into A, B, C, and D checks. Starting with A checks, which are the lightest aircraft inspections, these progressively become more detailed and intensive up to the D check. In 1987, the lubrication of the jack screw assembly was to be undertaken at every B check, which in Alaska Airlines' case was every 500 flight hours. In 1988, it was decided that B checks were no longer to be performed, and the tasks performed during B checks would be divided between the A and C checks. At this time, it was decided that the lubrication of the jack screw assembly would be completed at every 8th A check, or every 1,000 flight hours. This was an increase in the lubrication interval of 100%. In 1991, the time between A checks was increased from every 125 hours to every 150 hours. Lubrication of the jack screw assembly would still take place every 8th A check, which increased the time between lubrications to 1,200 hours. In 1994, that time between A checks was increased again to every 200 hours. This now meant it would be 1,600 flight hours between each lubrication of the jack screw assembly. In 1996, the lubrication of the jack screw assembly was removed from the A check altogether, and would now be determined by a set calendar duration of 8 months, regardless of how many hours the aircraft had flown. The investigators calculated that on average, this meant that the lubrication would be carried out every 2,250 flight hours. Thus, between 1987 and 1996, the lubrication intervals on the jack screw assembly had increased from 500 hours to up to 2,250 hours. Even taking the poor procedures to maintain the jack screw, and increasing maintenance intervals, this still does not fully explain how the Acme nut came to be in such poor condition. As well as being lubricated, the jack screw assembly was also supposed to be periodically inspected for wear and replaced as it wore out. Looking at the history of the McDonnell Douglas MD83, it is actually the evolution of an older aircraft, the DC-9, which was first introduced in the 1960s. When the DC-9 was introduced by Douglas, a sample of the aircraft were very closely monitored by the manufacturer. One of the outcomes of this monitoring was recognizing that the deterioration of the Acme nut was significantly faster than the designers had expected. To allow users of the aircraft to monitor acme nut wear without removing the entire jackscrew assembly from the aircraft, the manufacturer developed the on-wing end play check procedure. The procedure calls for pulling down on the horizontal stabilizer, using a restraining fixture to change the load on the jackscrew. Pulling down on the stabilizer allows movement, or end play, between the jackscrew and the acme nut threads. This play is then measured using a dial indicator, which is mounted on the lower mechanical stop, with a plunger set against the lower surface of the acme nut that measures the vertical movement of the jackscrew when the load is applied. The amount of end play is used as an indication of the amount of acme nut thread wear. The procedure calls for the restraining fixture load to be applied and removed several times until consistent measurements are achieved. If an end play reading of greater than 0.04 inches was recorded, the nut was to be replaced. In 1985, when Alaska Airlines maintenance procedure was approved by the Federal Aviation Administration, the end play checks on the jackscrew assembly were to be completed at every second C check, which amounted to every 5,000 flight hours. By 1988, C checks were increased to every 13 months, with no limit on the number of hours the aircraft could fly. The frequency of end play checks at every second C check remained the same. This meant that end play checks would be performed every 26 months. Based on the utilization of Alaska Airlines MD80s at the time, this corresponded to an end play check every 6,400 flight hours. In 1996, the C-check interval was increased again, now to every 15 months. This meant that the end play check would now be carried out every 30 months. But because the utilization of Alaska Airlines aircraft had increased due to the delay in purchasing new aircraft, this meant an average of 9,550 flight hours would pass between each check. All of the above changes were approved by FAA personnel. The last end play check on the MD83, which would become Alaska Airlines Flight 261, was performed in September 1997, more than 2 years before the final accident. The maintenance technician carried out the end play check on September 27th and noted that the end play was at the limit of acceptable wear, 0.04 inches. He noted that the next action should be to replace the acme nut with a new one. That mechanic was the same man who would go on to write to the FAA with his concerns on Alaska Airlines maintenance policies the next year, John Leotine. Over the next 2 days, the work cards the mechanics filled out indicated that they were going to order the replacement acme nut, and this may cause a delay of the departure of the aircraft back to service. On September 30th, the end play check was ordered to be carried out again by different personnel. This time, the test came back showing end play of 0.033 inches, which was acceptable according to the maintenance documentation. The tail was closed up without the acme nut being replaced and returned to service. When the NTSB studied the procedure that was used to perform the end play checks, they discovered that there were opportunities for errors which would cause the end play results to be inaccurate, including the calibration of the dial indicator, the knowledge of the mechanics on the procedure, and how the jackscrew was sitting within the acme nut. They did not consider the check to be very reliable, even when it was repeated several times. Perhaps most seriously, the investigators studied the restraining fixture which Alaska Airlines had been using to pull down on the horizontal stabilizer and perform the checks. The NTSB found that instead of using a restraining fixture produced by the manufacturer of the aircraft, Alaska Airlines had manufactured their own restraining fixture. According to one of the employees in charge of tooling at Alaska Airlines, what had been manufactured in-house was nowhere close to the tool which had been recommended. When the NTSB tested the fabricated restraining fixture, They found the tests consistently underread the level of end play. Thus, the 0.04 inches John Leontine had recorded, or even the 0.033 inch measurements, may have been found to be out of tolerance had the correct restraining fixture been used. During the federal grand jury investigation, the FAA uncovered numerous problems with Alaska Airlines maintenance procedures, which the NTSB believed they should have uncovered long before an investigation was necessary. In the year preceding the accident, 1999, the FAA was undertaking a transition to a new certification and maintenance oversight system, which was a challenging process. It reduced the amount of time the FAA personnel had to actually inspect the airline's maintenance procedures, as their time was spent introducing the new system. The FAA was also critically understaffed at this time. In November 1999, 2 months before the accident, a senior member of the FAA's maintenance oversight group responsible for Alaska Airlines wrote to his superiors. He stated that he required more personnel to adequately perform the inspections, and that if the FAA continued to operate with the existing limited number of airworthiness inspectors, diminished surveillance was imminent, and the risk of incidents or accidents at Alaska Airlines was heightened. All of these factors put the 88 passengers and crew members of Alaska Airlines 261 in an aircraft that should never have been permitted to fly. The failure of the horizontal stabilizer was catastrophic for the aircraft. With what we now know about the lax regulations and negligence that led to the aircraft being put in this position, we can now return to the cockpit and follow the last 80 seconds of Alaska Airlines Flight 261. It is 4:19 p.m., 9 minutes after Alaska Airlines 261 recovered from its initial dive. The pilots have just agreed to head towards LAX and land immediately without investigating the trim system any further. Suddenly, the pilots hear a series of quiet thumps. These are the sounds of the torque tube finally failing and beginning to be pulled through the acme nut due to the aerodynamic forces acting on the horizontal stabilizer. First Officer Tansky finds he suddenly needs to pull back on the control column with even greater effort and maintain their altitude as the horizontal stabilizer, freed from the bottom of the acme nut, begins to be pushed up. First Officer Tansky asks Captain Thompson, "Do you feel that?" Thompson replies, "Yeah." Tansky, flying the aircraft at this moment, says, "This is a bitch." A few seconds later, an extremely loud noise fills the cockpit and the cabin of the aircraft. While not 100% certain what this noise is, the investigators believe it is the sound of a wake vortex caused by the sudden high angle of attack of the horizontal stabilizer as it finally pivots completely backwards. The MD83 immediately lurches downwards and enters into an uncommanded steep dive, much steeper than before. Simultaneously, the aircraft starts rolling onto its back. Loose items bounce around the cockpit. Captain Thompson commands, push and roll, trying to counter the inversion that is developing, but the elevator appears to be completely ineffective. Despite the pilot's best efforts, the aircraft has completed its roll and is now flying inverted. Now the aircraft is flying level, even if upside down. This causes the initial rapid dive to slow somewhat, and gives the pilots time to assess the situation. Captain Thompson commands left rudder in an effort to rewrite the plane, but since both pilots are now upside down and suspended in their harnesses, First Officer Tansky cannot reach the left pedal. Captain Thompson instead orders right rudder. Both pilots push hard in an attempt to rewrite the plane, but Alaska Airlines 261 remains inverted, despite the pilot's best efforts. Assessing their situation, Captain Thompson states, "Are we flying? We're flying. At least upside down we're flying." The MD83's engines were never designed to operate upside down, and the right engine begins to suffer from compressor stall as the airflow into the engine is interrupted. The engine begins to spool down. In a last effort to arrest the descent, Captain Thompson orders the aircraft's speed brakes are deployed. As the Pacific Ocean rushes up to meet the aircraft, Captain Thompson states, "Here we go." A second later, the recording stops. For the passengers and crew of Alaska Airlines 261, the final descent took 80 seconds. 1 year after the accident, both Captain Ted Thompson and First Officer Bill Tansky were awarded the Gold Medal for Heroism by the Airline Pilots Association. This was only the 12th time the medal had ever been awarded since its introduction in 1952. It was also the first time the medal had been awarded posthumously. The pilot's decision to remain over the ocean to troubleshoot the aircraft, instead of heading over LAX where the plane might have crashed into a heavily populated area, was praised. Also praised was their level-headedness in the face of a terrifying situation, and their refusal to give up. Captain Thompson and First Officer Tansky tried to fly the plane the whole way down. NTSB board member John Goglia accurately summed up the loss of Alaska Airlines 261, stating, "This is a maintenance accident. Alaska Airlines' maintenance and inspection of its horizontal stabilizer activation system was poorly conceived and woefully executed. The failure was compounded by poor oversight. Had any of the managers, mechanics, inspectors, supervisors, or FAA overseers whose job it was to protect the mechanism did their job conscientiously, this accident cannot happen. The NTSB has made several specific maintenance recommendations, some already accomplished that will, if followed, prevent the recurrence of this particular accident. But maintenance, poorly done, will find a way to bite someone else." Thank you for listening to Inside the Black Box. Please remember to follow the podcast on Twitter at ITBB Podcast. That's India Tango Bravo Bravo Podcast. Please feel free to ask any questions on Twitter, and I will endeavour to answer them. Until next time.